Then when we go and interpret the sign chart for the inequality of that specific problem, we're going to be writing our answers in interval notation, just so we know. Think about endpoints. Okay, so first thing we do, set it equal to 0. So if I'm setting it equal to 0, what would my x-intercepts be?
-4, -1, 3.
Yes. Now let's make our sign chart. And put those x-intercepts on the sign chart. Oops, hang on. It's -4. I was thinking about the last problem still. Now for this inequality, can we equal, like looking at the actual inequality, are we allowed to actually equal 0? No, so what kind of circle do you think I'm going to put around these? Closed means filled in to me. Filled in means I can equal it. Open circle, so I'm open circling it because I cannot equal it. Okay, then I'm gonna number, you don't really have to do this, but just so you understand where I'm getting these numbers from, I'm going to number the intervals in between these x-intercepts. So this maybe is 1, 2, 3, 4. So I have 4 intervals that I'm gonna test. Really, once you start to understand the behaviors of polynomials, you kind of only have to test one of the intervals. If you look at this polynomial, and then you can tell how it's going to be passing through each of these x-intercepts, so you can kind of tell how the behavior is going to end up being. But we'll test all of them just for our friends who don't intuitively understand these types of things. Okay, what is a number in interval 1 that might be easy to plug in? -2 is not in interval 1. Interval 1 is everything smaller than -4. I heard -6. -5 would also work. -100 would also work. One of my mentor teachers always used 12 and -12 because that was her daughter's birthday. She was born on 12/12 in 2012. So we had a lot of 12s in our practices. But I like to usually use a number near the x-intercept because then the value is going to be like 1 or -1, depending. But again, you do you. The number does not matter. It's just whether it's a positive number when I plug this in or a negative number. So I'm going to plug in -6. We are trying to determine, do we get a positive number, something greater than 0, or a negative number? Let's see. But -6 minus 3, is that positive or negative? Negative. I don't care what it is. -6 plus 1, positive or negative? Negative. -6 plus 4, positive or negative? Negative. Okay. So we got a negative times a negative is a positive. Times another negative, what does that become? Whatever negative number. Is a negative number bigger than 0? No. So because the negative number is not bigger than 0, and the question was asking to find all of the y values bigger than 0, we are not going to shade. So we are not shading interval 1. Because that is where this polynomial is not bigger than 0. Okay, now a number between -4 and -2. Oh, -1, I mean, sorry. Someone said -2 earlier, so I was trying to... -2, there we go, okay. -2. -2 is in this interval. Okay, negative 2 minus 3 is negative. Negative 2 plus 1 is negative. If you ever get a 0, that's because you picked an x-intercept. You need to pick something between the x-intercepts. Okay, then this one is positive. A negative times a negative is a positive, times this positive is a positive. So is this number bigger than 0? Yes, because all positive numbers are bigger than 0. So what are we going to do? Shade 1. What I mean by shade is like, you know, something like that. Like a little squiggle. So already your answer could be, we go from negative 4 to negative 1, and there might be another place where the function's positive. So from negative 4 to negative 1, I have parentheses. Why do I have parentheses on negative 4 and negative 1? Because it's greater than not equals to. So parentheses, because it was not equals to. What is a glorious number between negative 1 and 3 that we would maybe want to use? 0 would be the number I would choose, because then I just have to look at the signs. So plugging in 0. This you could probably do in your head, but I'll just write it down so that you have it in your notes. Okay, 0 minus 3. Negative 3. Oh, wait, I said I don't care about the number. Okay. Times 0 plus 1. Positive. Times 0 plus 4. Positive. Well, what does this end up with? A negative. And a negative is not bigger than 0, so no shade. All right, last but not least, pick your favorite number bigger than 3. I'm going to pick 33. That's my favorite number. 33 minus 3. 33 plus 1. 33 plus 4. You pick a different number if that's not your favorite number. We got all positives. Positive times positive times positive equals a positive. We are shading 4. Region 4, everything greater than 3. Where am I shading on the right side? Where's this shading to? Infinity. So I'm going to go from 3 to infinity. Don't usually like to circle my answers, but I feel like it kind of got mixed in my work there. So that would be my final answer. That is where this is positive. Now, I said some of you are going to be able to figure this out once you figured the first interval was positive or negative, based on how the polynomial would look. So at negative 4, if I were to graph this, would I have kissed or crossed it? Crossed. How about at negative 1? How about at 3? They all were crossing. None of them were bouncing. So all of them, between all the x-intercepts, were switching signs because they were going from negative to positive if I'm crossing, and then back around, going from positive to negative if I'm crossing, turn it back around, negative to positive. You could have figured out the sign of each of those by like understanding what we were doing the other day with the kissing crossing. That being said, try to work on example 5. You may work with your table. Think about what's happening at negative 2. Look at its multiplicity. Mm-mm. What's the sign saying? We want this side to be smaller than 0. So smaller than 0 is negative. All right, at x equals -2, what type of multiplicity does it have, an even or odd? Even. So at even multiplicities, the behavior will always match on either side of it. So the behavior on interval 1 is going to be the same as the behavior on interval 2. They will either both be positive or both be negative, because it's like either bouncing this way, going down on either side of it, or bouncing up. So they're either both positive or both negative because it's an even multiplicity. So I'm going to plug in 0 because that's an easier number to plug in my opinion. Also, no matter what I plug into this, what will always come out if it's squared? What's -4 squared? Is it -16 or +16? So no matter what's in there, it's always positive. That part is always positive. It's the other part, the 5, that's going to make this be positive or negative. So we kind of knew at 2, no matter what I plugged in, would be positive or negative. So really, you don't even have to plug into that point because you kind of just know this is like a permanent positive. That's kind of what I meant to say. I think that you're thinking that root is going to be positive. But I mean, no matter what I plug in, it's always going to be a plus. So I don't even have to think about plugging into that part because it's always positive. Or just plug in, follow your heart. So we got positive times negative. That is negative. Is a negative number less than 0?
Yeah.
Yes. So we are going to shade. Remember, it's not always whether it's positive. You got to look at the sign of the problem. Oh, I forgot. I didn't make my bubbles. So at negative, my circle at -2, am I filling it in or not? Yes, we filled in circles because it's an equals 2. Filling in my circle. I can equal -2 and I can equal 5 because I can equal 0. And then we said we're shading. Now, if we know our behavior already, we're saying this is positive. Nope, we're saying this is negative. Sorry, I forgot what sign we had. Negative, and then at 5, what has to happen then? It has to go through it because 5 has an odd multiplicity. So we kind of already know that interval 3 is going to be positive. But if you're not sure, plug a number in interval 3 and test it. Yeah.
So was there not also a +2 on the x-axis?
Mm-mm.
It's like x + 2 squared and then
It just means like x plus 2 happens twice. It's not x plus 2, x minus 2.
oh,
X plus 2, x minus 2 would have factored from x squared minus 4. But this foils into x squared plus 4x plus 4 when you like FOIL it out or distribute it out. Some teachers hate when people say FOIL. All right, so this is always going to be positive no matter what we put in there because it's squared. And then 6 minus 5 is also positive. Positive is not smaller than 0, so we are not shading. No shade. Here's another thing that I definitely wanted to make sure I pointed out to you guys after grading your first quizzes. We don't actually have a gap here. There's not, can I equal -2? Yes. So we're going from negative infinity all the way until 5. we're not going to go around -2. We are linking those together. There's no break in them. So we're going from negative infinity all the way to 5. What is 5 going to have? Parenthesis or bracket? Bracket, because it's a filled in bubble or an equals to in the sign. If, for example, let's just like write a if you had -2, open circle, and 5, open circle, and you shaded it like this, would I have to break between -2 on either side? Yeah, because you can't actually equal -2. So this one would have been like -2 parenthesis, -2 to 5 parenthesis. Okay? That's not like the answer to this problem. That's just like if you come across that. All right, so checking the chunks is kind of, I think, hard at the beginning because you're like, wow, this is new. This is something I've never maybe done before. But once you get the hang of it, it's just really plugging in values in between the x-intercepts and checking their signs. This is something that's so important when you get to Calc AB. That in Calc AB, this is how we determine whether a function's increasing or decreasing. We look at the derivative and see where the derivative is negative. That's its slope. So where the derivative is negative, the function's decreasing. It's like a huge part of calculus. All right, even and odd functions. This is kind of another thing that is nice in pre-calc that helps you be able to make your life easier in calc. So an even function specifically is where we have y-axis symmetry. So even function has y-axis symmetry. So with an even function, whether I have a positive input or a positive output, they equal the same thing. So let's look at 1. At 1, x equals 1, the y value is -1. At x equals -1, the y value is the same thing because it has y-axis symmetry, meaning I can go fold this paper on the y-axis and they would all touch each other. That's y-axis symmetry. You can also tell without, if it's a polynomial, remember polynomials have positive integer, so whole number, exponents. So if it's a polynomial, all degrees should be even. So if all the degrees are even, it's an even function. So looking, we have 4, 2. What's the degree of a constant? 0. Technically, we'll say 0 is even because of the pattern going like 0, then an odd number, then 2, then an odd number 3. Yeah, so 0 we'll say is even. So this is an even function. You also could have plugged in negative x. And if I do negative x to the 4th minus 8 times negative x squared plus 1. Negative times a negative is a positive, and you do that twice with the 4th. And you get the same thing you started with. If no sign changed, we'll say same signs. If no signs change, then it's even. If all of the signs change, then it's odd. Or you can just look at the degree if it's a polynomial. So let's look at an odd function. Odd functions have origin symmetry. Origin symmetry means that we fold along the x and the y. So if I could fold it along the x-axis and then again along the y-axis or vice versa, that's origin symmetry. So in origin symmetry, opposite inputs have opposite outputs. So this sign negative x should have the opposite output as when I plug in positive x. Let's look at one that actually has a sign. None of these are crossing all that helpfully. Like -3 is 0, so that's not going to show you. Let's say 2. 2 looks like it's actually on. Okay. So if I'm looking at -2, -2 is at 2. It's opposite input, so the opposite sign would be +2 for the x. The output is opposite. So what I mean by opposite inputs, I'm talking about the -2 and +2. And then opposite outputs, I'm talking about going from +2 to -2. If you're given a polynomial, looking at the degrees, all the degrees are odd in an odd polynomial. But if you actually did the whole plug and chug thing, plugging in -x, negative times negative times negative keeps it being -x cubed. -9 times -x is a +9x. All the signs change. We went from a positive x cubed to a negative x cubed. We went from a -9x to a +9x. So that means all the signs change. If only one of them changed and the other one didn't, it's neither. Everett?
So if so like let's say for -9x, we know there's a 1 over the x.
Mm-hmm.
But if it's just a whole number with no x, then the degree is 0.
Mm-hmm. And that we're thinking is even.
Why do we count the 0 as even?
Because the next number next to it would be odd for being 1. All right, determine the polynomial even, odd, or neither. So on A, what do we think? Even. Oh my gosh, I keep doing it. I want a pen. We're saying even. All right, B, what do we think? No. Neither. It has odd for the first two and then even for the last one, where this one was all even. All right, now we're looking at the graph. How about C? Odd. It has origin symmetry. How about D? Neither. It is symmetric about x equals 1, but it's not symmetric about y-axis or the origin. I don't want to say it has no symmetry, because it is symmetric about like its axis of symmetry, because it's a polynomial, but that's not the type of symmetry we need. Okay, I think we can zip through 1.6. Let's go. We're zipping and zapping. Okay, so end behavior. We've already done this. This is kind of why I think this is going to go fast. The end behaviors of a function describe how a function behaves as it moves infinitely to the left or the right. In other words, the end behavior is what the values of y or f of x are doing as x is increasing or decreasing without bound. So as x is going, because we're going to actually need this soon, I'm going to describe. As x increases without bound would be x going to positive infinity. X decreases without bound is x going to negative infinity. So today we're going to introduce limit behavior. I'm not sure if you did that in Algebra 2. Limit behavior is definitely like FRQ 2 A I think, or no, it's BII. So you will have to write a limit behavior of an expression on the free response questions and on multiple choice, but you'll actually have to, like, in your handwriting, write the limits. So we're going to do verbal and then using notation. So looking at the left behavior verbally. So left behavior would mean as x, or the input value, decreases because it's going to the left without bound, the y's, the outputs, what are the y's doing as we go to the left? Increasing without bound. Almost put pound, bound. Okay, so this is our first time writing a limit statement. How exciting. What a time to be alive. In a limit statement, every limit statement is going to have these components. You're going to write LIM. It can be cursive because if you're fancy. Then you name the function. We'll just name this one f of x. So these are like key features of a limit statement. They all say LIM for limit, and then right next to LIM is going to be whatever the name of the function is. Then underneath the limit, so right underneath LIM, you are writing x going to infinity or negative infinity or whatever you're trying to do the limit towards. So in this case, we'll say x goes to negative infinity because it's decreasing without bound. Then we put an equals to sign. We said it was increasing without bound. So y was going to positive infinity as x was going to negative infinity. You are not saying x arrow negative infinity, y arrow infinity. You have to put it in limit notation for this form. So try to do the right verbal and right limit. All right, hopefully you had something that says as x increases without bound, the y's decrease without bound. So your right limit statement what should the x be doing now? Positive infinity. And then the equals should be negative infinity. Okay. I don't feel like writing a lot more because we're kind of running out of time. Let's just do the limit behavior for this one. So limit statement for B. Left would be negative infinity. So on your classwork or homework, you could just go through and anywhere that says left, write LIM x negative infinity. And anywhere that says right, say LIM positive infinity. Okay, so on the left side, what is it doing? Going up, what does that mean? Right, so the y's are going to positive infinity. The right side's also going up, so what does that mean? Yes, so we're going As x's are increasing, y's are increasing without bound. As x's are decreasing without bound, the y's are increasing without bound. Yes?
So when it comes to doing the left or right, do you basically just like split it where like down the middle, or where you think it's supposed to be split?
No, we're looking at its end behavior. So this is x going to negative infinity.
But it's like, you see how like it's like going down then up. Like you're going from, I'm assuming, like basically where it's 1/2 over to the left. Do you understand what I'm saying? Kind of like.
Sure,
okay.
yeah, but it's just really the ends because it could do any kind of wiggling in between, and then we're talking about the end. All right, and ooh, my example 2 words got scooched on the page. How sad. Okay, example 2, sketch the polynomial with the given end behavior. The only thing we're sketching is its end behavior. Anything in between, you can just connect them however you want. So I want you to put your end behaviors in. Don't just blindly copy me. So put some end behaviors on based on the limit statements. And then connect them however you want. Maybe not just a straight line. Some kind of wiggles. So for A, what should your end behaviors be doing? Both going down. So you can do a parabola if you're boring. You can do like an N if you wanted to spice things up a little bit. It's both going down. Not bad, that's not. That was cute, good idea. I'm shocked. It's because it's from Buc-ee's. The beeve never lets you down. All right, so I saw somebody's very cutesy idea that did this. Breast cancer ribbon, not a function. Okay, this is not passing the vertical line test. For each input, we don't have exactly one output. But anything else, doing something like that. Oh, whoa, nothing showing. Okay, the lag is crazy. Something like that, wow, cool. But that, great. All right, now over here, B, we got the left side, you should have had going down, right side going up. And again, we're not swooping through and doing like that because that's not a function. It would be so much cooler. When we get to polar, we can do stuff like that, but not right now. All right, and I think we're almost done now. No, okay. A polynomial end behavior. Polynomial equation. It's easiest to find the end behavior, to me, on the right side first. The reason for that is the right side is affected by the sign. The sign of the leading coefficient. So the right side is using the sign of the leading coefficient. So it goes up. The right side goes up, or to positive infinity, when the leading coefficient is doing what? Positive or negative? Positive. The right side goes down, or to negative infinity, when the leading coefficient is negative. The left side is affected by the degree. So the left side is the degree of the leading term. So the left side, if the degree is even, will the left side match or go opposite? Match, or be the same. And then if the degree is odd, the left side goes opposite. So let's look at example 3. Determine the end behavior. Limit notation is not necessary. Helpful. Okay. So looking at This one, we have a positive. So my right branch is going up. All of B is also positive, so my right branch is going up. What's on C? What am I going to do? Right branch is going down because it's negative. Okay, then on A, let's think about the left branch. We got odd. We got odd degrees, so what should the left be doing? Opposite, so we're going down. We got an even degree, so the left side's matching. And we got an even degree here. There's not an additional x in the front, so I don't have to like multiply. It's gonna go same. So this is going opposites. Negative, positive, 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 negative, negative. All right, D through F is getting a little trickier. I want you to think for a second before I zip through it. Yep,
Is it class rich? Just the odds?
we'll talk about it. Yep,
Wouldn't the right C also be negative?
they're both there. Oh, sorry, thank you. D as in, don't screw it up. We got the right side, what is it doing? Down. Left side, what is it doing? Opposite, so it's going up. Opposite because it's odd. Hey, look, they both start with the same letter. That's crazy. All right, looking at E. Oh, is it up, up? Because I have a negative or a positive 8x squared. Oh, dang, it tricked me. It is based on the biggest degree. I'm not adding all the degrees up here because this is in kind of in standard form. It's all foiled out. I'm just looking at the biggest degreed term. So we got a negative. The right branch should be going down. And it's odd, so the left branch should be opposite. Okay, F is, I think, the hardest question because it is not in standard form. It's not foiled and it has multiple x's, unlike C. So if I did foil this out, I would have the 2x would distribute in and give me x squared, and then these would multiply together also and give me x cubed, but what else would it have? It would be a negative x cubed. Why is it a negative x cubed? Technically a negative 2x cubed. This negative in here, if I foil these out, would turn the whole expression negative. If there had a negative in front, it would also have affected the sign. So really, its leading term, the only one we actually care about, is negative 2x cubed. Negative, positive. All right, I think you guys can do example 4, and when you finish 4, get out a calculator or your Desmos. A calculator or Desmos, so that means computer. Yep. Mm-hmm. Yep, we need a left and a right.
How do we differentiate the left one from the left right?
How do you think? What's the left x going to?
Well, I know the difference, but I mean, like, when we're writing it down, like, do you want us to write, like, left for one of them?
Nope. So you would have negative infinity. I can read and see that you are doing the left.
Okay.
If you wrote them in a different order, then I just have to be like making sure I'm really looking at it. Usually I do the left one first just because I read from left to right. And I think about it from left to right, but you do your... Pay attention on B. What's the function name for B? G of x is not f of x this time.
So this is roughly the clip is not. JJ.
Jacob, did you use the clip?
I can see it.
Okay, go ahead. I'll just show you. Find the clip. All right, so example 4, we should have had negative infinity after our limit statements. And then we would have had negative infinity, positive infinity. Now let's put these in Desmos. Remember, on the AP exam, you will be able to have a handheld calculator and be able to use Desmos. So follow your heart. If we are using the handheld calculator, that will take more steps and I will help you. But on Desmos, you can just type this in. I think you'll get there fast. So you can get out your Chromebooks if you would prefer. Y equals x squared minus 3x plus 1. What's the end behavior for this one? Positive. Gets a little trickier when we need the fraction. Not that tricky though, you just put a division sign and Desmos opens up a fraction for you. But I'm gonna help the people who got their calculators, and I feel like the Desmos is a little bit easier. Alright, so for A, you need to type in y equals on, like press the y equals button for A. And B and C. All right, so once you type the y equals, then we put the variable button, squared. So unfortunately, just pressing this button does not make x squared appear. It just squares whatever thing you're trying to square. X squared minus, I can zoom out a little bit, minus 3, variable button, x plus 1. And then you can look at the calculator by graph, or looking at the graph by pressing graph. Mine's very zoomed out. I can tell by looking at how bold the axes are. I want to show you how to put a fraction in here. So if we go back to y equals, I press clear to get rid of all of it. Do you see, I'm showing it on the screen, where a fraction might be? You see how it's green? So you press the green button to get there. You're gonna alpha variable button. And then you're gonna type in 2x minus 3, x plus 1. Bruh. All right, my graph is so zoomed out, I really can't tell what's happening. What I can do, I can press to the right. Oh, I can press trace, and then go to the right. And look at my y values. Oh, they start being fractions, but they're like 1.86. Fraction. Let's get to another decimal, maybe. Or it'll never become a decimal again. Cool. It's approaching 2 towards infinity. It also should be approaching 2 on the other side. If you're not sure, oh, here's a fun fact about your calculator. On the calculators, if you want to plug something in, you can go to second trace value, but you can also do alpha trace. I typed my equation into y1, and And then I can open up parentheses and say, I want to find this at 1,000. And then it gives me a fraction, which isn't super helpful. I can press math, go down to decimal, and it'll take my answer and make it a decimal. Do you see how close to 2 that is? 1.995. It's really close to being 2. It keeps, usually if you input something as a fraction, it's going to output as a fraction. If you knew your horizontal asymptote rules, which we haven't gone over, but you did do it in Algebra 2, you could have known what this one was approaching. The graph here, I'm just going to sketch it to put on our thing. Yep.
In this house, once you get to the moon, it just hits 2.
Yeah, it's basically 2 after that. It's like 1.99999. Yeah. It has a horizontal asymptote that it's approaching at y equals 2. It's because it's approaching a horizontal asymptote of 2 on both sides. That's what its limit is going to be. Oh, that's an infinity, hello. And then this one has a horizontal asymptote at 0. And its graph looks like this. So again, going to negative infinity. For h of x would be approaching 0. The limit as x approaches infinity of h of x would be also 0. I didn't graph it very well, but that's going to the horizontal asymptote. Okay, we got a lot to practice today. I think on 1.5, if we get back out 1.5, we only did 1 through 7. Odd. So for 1.5b classwork, and if you don't have the paper with you, it is posted on Google Classroom, so you can like write on this paper. That would be so fun for you. We're gonna do 10. 16, 22, 24, 27, and I'm putting a star by it because I always like to ask questions like 27 on the test. 28A, 1.5B, seeing as I wrote 1.5. And then we're looking at the next page. Let's see. We're finishing the graph to make it look odd or even. So we're going to do 30, 31. I think you get it just there. And we'll do 38. Okay, then on 1.6, much faster. Can you tell which section I care more about? I mean, I care about 1.6, but it's just limit and behavior. 1.5, definitely like the Mac Daddy section of this entire unit. It's kind of a culmination of all the things. You might be able to finish 1.6 first if you want to do that one first and get it stamped. Just an idea.